Hello friends, welcome to our channel, Gajpal A Learnag. In this video we are going to study about the topic acid-base titration. This is the part of pharmaceutical analysis. So let's start. First let's see about introduction of the acid-base titration. Acid-base titration is a fundamental analytical technique used in chemistry to determine the concentration of an acidic or basic solution. This method involves the controlled addition of a solution with a known concentration, titrant, to a solution with an unknown concentration, analyte, until a neutralization reaction occurs. The point at which the reaction is complete is known as the equivalence point, and it marks the stoichiometrically balanced ratio of acid and base in the solution. The primary principle underlying acid-base titration is the concept of neutralization, where an acid reacts with a base to form water and a salt. This reaction is often represented by the general equation, acid plus base to give salt plus water. The most commonly used indicators in acid-base titrations are pH indicators, which change color at a specific pH range. The color change indicates the endpoint of the titration, which is often close to the equivalence point. However, in more precise titrations, pH meters are used to monitor the pH of the solution in real time, providing accurate data to determine the equivalence point. There are several types of acid-base titrations, including: first, strong acid, strong base titration. In this type of titration, a strong acid is titrated with a strong base, or vice versa. The equivalence point occurs at a pH of 7, which is neutral. Second, weak acid, strong base titration. Here, a weak acid is titrated with a strong base. The equivalence point is reached when the pH is slightly above 7 due to the presence of the conjugate base from the weak acid. Third, strong acid, weak base titration. In this case, a strong acid is titrated with a weak base. The equivalence point is below pH 7 due to the presence of the conjugate acid from the weak base. Fourth, weak acid, weak base titration. This is a more complex scenario involving the titration of a weak acid with a weak base. The equivalence point and the pH depend on the strengths of the acid and base being used. To perform an acid-base titration accurately, precise measurements of both the titrant and the analyte are crucial. The process involves gradually adding the titrant to the analyte while monitoring the pH or using indicators to observe color changes. The point at which the indicator changes color or the pH reaches a specific value indicates the endpoint of the titration. This information is then used to calculate the concentration of the analyte based on the known concentration and volume of the titrant used. Next is theories of acid-base. First, Arrhenius theory of acid and bases. The Arrhenius theory, formulated by Swedish chemist Svante Arrhenius in the late 19th century, is one of the earliest theories of acids and bases. It provides a conceptual framework for understanding acid-base reactions and their behavior in aqueous solutions. According to the Arrhenius theory, acids and bases are defined based on the ions they produce when dissolved in water. A. Arrhenius acid. An Arrhenius acid is a substance that, when dissolved in water, increases the concentration of hydrogen ions, H+, in the solution. In other words, it donates H+ ions. These H+ ions are also often referred to as protons. The classic example of an Arrhenius acid is hydrochloric acid, HCl, which dissociates in water to produce H+ ions. HCl to give H++ Cl-. B. Arrhenius base. An Arrhenius base is a substance that, when dissolved in water, increases the concentration of hydroxide ions, O-, in the solution. It donates O- ions. An example of an Arrhenius base is sodium hydroxide, NO, which dissociates to yield O- ions. NaOH to give Na+, plus OH-. C. Neutralization reaction. The Arrhenius theory also explains the concept of neutralization reactions, where an acid reacts with a base to form water and a salt. This occurs because the H+ ions from the acid combine with the O- ions from the base to form water, 2H2O, while the remaining ions combine to form a salt. 2H++ plus OH- to give H2O. Now, limitations of the Arrhenius theory. Certainly, here are the limitations of the Arrhenius theory of acids and bases explained in points along with examples. First, limited to aqueous solutions. The Arrhenius theory is primarily applicable to aqueous solutions and doesn't account for the behavior of acids and bases in non-aqueous solvents. For instance, ammonia, 3NH3, is a base in the arrhenius sense due to its ability to generate OH- ions in water, but it behaves differently in non-aqueous solvents. Second, doesn't explain acid-base behavior in solvents without water. The theory fails to explain the behavior of acids and bases in solvents other than water. For example, hydrogen chloride, HCl, dissolved in liquid ammonia, 3NH3, does not follow the arrhenius behavior, even though HCl is an arrhenius acid in water. Third, limited to H plus and OH minus ions, the arrhenius theory focuses solely on the presence of H plus and OH minus ions, neglecting other important species involved in acid-base reactions. An example is the reaction between acetic acid, CH3COOH, and ammonia, 3NH3, where CH3COOH donates a proton without producing H plus ions. Fourth, no explanation for amphiprotic substances. The theory struggles to explain substances that can act as both acids and bases, known as amphiprotic substances. For instance, water, H2O, can donate H plus ions as an acid and accept H plus ions as a base, but the arrhenius theory doesn't account for this behavior. Fifth, excludes basic substances with no OH- ions. The arrhenius theory incorrectly categorizes substances that can neutralize acids but do not produce OH- ions. An example is aluminum hydroxide, 3Al-OH, which can neutralize acids but does not dissociate to produce OH- ions. Sixth, doesn't address acid-base reactions in gaseous phase. The theory does not provide insights into acid-base reactions that occur in the gaseous phase. An example is the reaction between hydrogen fluoride, HF, gas and ammonia gas, 3NH3, which forms ammonium fluoride, NH4F, without producing H plus or OH- ions. Seventh, limited to simple proton transfer. The arrhenius theory primarily focuses on the transfer of H plus ions as the defining characteristic of acids and bases. It does not encompass more complex reactions involving electron pair transfers. An example is the reaction between hydrogen sulfide, H2S, and hydrogen cyanide, HCN. 8. Inapplicable to superacids and superbases. The theory struggles to explain substances like superacids and superbases that display extreme acid or base behavior, far exceeding the H plus or OH- concentration present in water. Second theory of acid-base titration is bronsted-lowrey theory of acid-base titration. The bronsted-lowrey theory of acids and bases, proposed independently by Danish chemist Johannes Bronsted and English chemist Thomas Lowrey in the early 20th century, provides a more comprehensive understanding of acid-base reactions compared to the arrhenius theory. The Bronsted-Lowrey theory defines acids and bases based on their ability to donate or accept protons, hydrogen ions, in chemical reactions, without being restricted to aqueous solutions. This theory extends the concept of acids and bases beyond the limited scope of H plus and O minus ions. A. Bronsted-Lowrey acid. According to the Bronsted-Lowrey theory, an acid is a substance that can donate a proton, AH plus ion, to another substance. In this context, the acid is referred to as the proton donor. When an acid donates a proton, it forms its conjugate base. For example, hydrochloric acid, HCl, can donate a proton to water, H2O, to form the hydronium ion, H3O+, which is its conjugate base. HCl plus H2O to give H3O+, plus Cl-. B. Bronsted-Lowrey base. A Bronsted-Lowrey base is a substance that can accept a proton, AH plus ion, from another substance. The base is referred to as the proton acceptor. When a base accepts a proton, it forms its conjugate acid. For instance, ammonia, NH3, can accept a proton from water to form the ammonium ion, NH4+, which is its conjugate acid. NH3 plus H2O to give NH4 plus OH. Now, conjugate acid-base pairs. In Bronsted-Lowrey acid-base reactions, there is a relationship between the acid and its conjugate base, as well as between the base and its conjugate acid. These pairs are called conjugate acid-base pairs. In a reaction, when an acid donates a proton, it becomes its conjugate base, and when a base accepts a proton, it becomes its conjugate acid. The equilibrium between these pairs is crucial in understanding the dynamics of acid-base reactions. Next, titration in Bronsted-Lowrey theory. In acid-base titrations based on the Bronsted-Lowrey theory, a solution containing an acid is titrated with a solution containing a base, or vice versa. The endpoint of the titration is reached when the moles of acid are equal to the moles of base, or when the acid and base are in their stoichiometric proportions. This corresponds to the point where the concentrations of the acid and its conjugate base, or the base and its conjugate acid, are equal. Limitations of Bronsted-Lowrey theory of acid-base. Certainly, here are the limitations of the Bronsted-Lowrey theory of acids and bases explained in points along with examples. First, doesn't account for non-proton transfer reactions. The Bronsted-Lowrey theory focuses on proton transfer as the defining characteristic of acid-base reactions. It does not adequately explain cases where acid-base reactions involve electron pair transfer without a proton being transferred. For instance, the reaction between ammonia and boron trifluoride, BF3. Second, limited to solvent with protons, hydrogen ions. The theory is most applicable to solvents containing protons, like aqueous solutions. It doesn't fully address acid-base reactions in solvents that lack protons, like non-aqueous or protic solvents. For example, in reactions involving Lewis acids and bases in non-aqueous solvents. Third, ambiguity in autoionization of water. The concept of autoionization of water, H2O rightwards harpoon over leftwards harpoon H+, plus OH-, raises questions about what should be considered an acid or a base. The theory doesn't clearly define which species is an acid or a base in this autoionization process. Fourth, challenges with very weak acids and bases. The theory struggles to explain very weak acids and bases that barely undergo proton transfer reactions. Substances like water, which acts as both a weak acid and a weak base, can pose difficulties in interpretation. Fifth, no explanation for amphiprotic substances. The Bronsted-Lowrey theory doesn't fully address amphiprotic substances, which can donate or accept protons depending on the context. Water is a prime example of an amphiprotic species, as it can act as an acid by donating a proton and as a base by accepting a proton. Sixth, limited to single proton transfers. The theory primarily deals with single proton transfers. It may not fully explain reactions where multiple protons are transferred simultaneously, like in polyprotic acids such as sulfuric acid, 4H2SO4. Seventh, no explanation for acid-base strength. The Bronsted-Lowrey theory doesn't inherently provide a quantitative measure of acid or base strength. It doesn't predict the extent to which a proton transfer reaction will occur. This limitation led to the development of the concept of acid dissociation constant, Ka, to quantify acid strength. 8. Excludes acid-base behavior of ions. The theory does not explicitly address the acid-base behavior of ions. For example, the behavior of H+ ions, which are central to the theory, isn't discussed within the theory itself. Third theory is Lewis theory of acid and bases. The Lewis theory of acids and bases, formulated by American chemist Gilbert N. Lewis in the early 20th century, represents a significant advancement in our understanding of acid-base interactions. Unlike the Bronsted-Lowrey theory that centers around proton-hydrogen ion transfer, the Lewis theory focuses on the sharing of electron pairs between molecules as the basis for acid-base reactions. This broader definition allows the theory to encompass a wider range of reactions and species, providing a comprehensive perspective on chemical interactions. A. Lewis acid. In the Lewis theory, an acid is defined as a substance that can accept an electron pair. This electron pair acceptor can be any atom, ion, or molecule that has an electron-deficient site, usually an empty orbital, capable of forming a coordinate covalent bond. When a Lewis acid reacts with a Lewis base, it shares the electron pair from the base. Common examples of Lewis acids include metal cations, positively charged ions, and molecules with vacant orbitals. For instance, aluminum chloride, AlCl3, acts as a Lewis acid when it reacts with a molecule of chlorine, Cl2, to form a complex. AlCl3 plus Cl2 gives AlCl4-. B. Lewis base. In the Lewis theory, a base is defined as a substance that can donate an electron pair. This electron pair donor can be any atom, ion, or molecule that has an electron-rich site, typically a lone pair of electrons. When a Lewis base reacts with a Lewis acid, it shares its electron pair with the acid. Common examples of Lewis bases include molecules with lone pairs such as ammonia, NH3, and water, H2O. For example, in the reaction between ammonia and boron trifluoride, BF3, ammonia acts as a Lewis base by donating a pair of its electrons to form a coordinate covalent bond. NH3 plus BF3 to give NH3.BF3. Now, coordinate covalent bond. In the Lewis theory, acid-base reactions often result in the formation of a coordinate covalent bond. This type of bond is characterized by the sharing of a pair of electrons, where both electrons come from one of the reacting species. This is in contrast to typical covalent bonds where each atom contributes one electron to form the bond. Next is advantages of the Lewis theory. The Lewis theory of acids and bases provides a more inclusive framework for understanding chemical reactions. It extends the concept of acid-base interactions beyond proton transfer, allowing for the explanation of reactions involving species that don't have protons, such as metal cations and non-aqueous solvents. Additionally, the theory can be applied to a broader range of reactions beyond traditional acid-base reactions, such as complex formation, coordination chemistry, and even the behavior of transition metal complexes. Last is limitations of Lewis theory of acid-base. Certainly, here are the limitations of the Lewis theory of acids and bases explained in points along with examples. First, doesn't provide a quantitative measure of acidity and basicity. The Lewis theory does not inherently offer a quantitative measure of the strength of acids and bases. While it can explain why certain molecules act as Lewis acids or bases, it doesn't predict the extent of their reactivity. Second, limited explanation for proton transfer reactions. The theory does not explicitly account for the common proton transfer reactions that are central to the bronsted-Lowrey theory. While it can still explain them within its framework, this might not be its primary focus. Third, excludes water's amphiprotic behavior. The Lewis theory doesn't provide a straightforward explanation for water's amphiprotic behavior, its ability to donate and accept protons. This behavior is more explicitly addressed by the bronsted-Lowrey theory. Fourth, challenges in classifying some molecules. There can be cases where classifying certain molecules as exclusively Lewis acids or bases is challenging. For instance, molecules with multiple potential electron donor or acceptor sites might not have a clear classification. Fifth, not as intuitive for aqueous solutions. While the Lewis theory can be applied to aqueous solutions, it is less intuitive in this context compared to the bronsted-Lowrey theory. It might not provide a simple explanation for phenomena like pH changes in water. Sixth, overlooks acid-base behavior in gas phase. The theory doesn't inherently address acid-base interactions in the gas phase, where electron pair donation and acceptance play a significant role. Seventh, complexity in complex formation. While the theory can explain complex formation, it might not always give an intuitive understanding of how the electron pair sharing leads to the specific geometries and properties of the complexes. Eighth, challenges with predicting reactivity. Predicting the reactivity between potential Lewis acid-base pairs can be complex, as it requires an understanding of both the electron pair donating ability of the base and the electron pair accepting ability of the acid. Ninth, no clear explanation for acid-base strength trends. The Lewis theory doesn't inherently explain trends in acid-base strengths across different substances, which is more readily addressed by theories like the bronsted-Lowrey theory and quantitative measures like pKa values. 10th, doesn't address acid dissociation constant, Ka, and base dissociation constant, Kb. The Lewis theory doesn't provide an inherent explanation for the concept of Ka and Kb values that quantify the extent of ionization of acids and bases in solution, respectively. Thanks for watching this video. If this video was helpful, then kindly please subscribe the channel and hit the bell icon. Thank you.